Welcome to this talk on MAIHDA, a new exciting approach for estimating intersectional inequalities and individual outcomes. So let's get going with the talk. So this talk is going to be three parts. I'm going to start by giving an introduction to MAIHDA with an empirical example from the literature. That will go over the basics, but we'll also set up the second part of the talk, where I will look at some of the statistical advantages of MAIHDA, and I'll compare the predicted intersectional inequalities from MAIHDA with simple descriptive statistics. Now, the third part of that talk is going to then talk about extending MAIHDA to move beyond just describing intersectional inequalities and individual outcomes to try and look at how regression relationships and specifically the effects of interventions differ across different intersections. So it's going to be a fine-grained, nuanced moderation or subgroup analysis that I'm thinking that MAIHDA could be used to do, and I'll kind of walk through in a kind of more conceptual level that. Okay, so part one. So what on earth is this MAIHDA thing? But before we get into that, we've got to get into what is intersectionality, because that is what has motivated the development of MAIHDA, and many applications link back to it, although it's not strictly necessary. So here I kind of stray away from my comfort zone of quant methods to talk a little bit about theory. So it's one slide, and let's hope I do this sufficiently well. So intersectionality, it's an area which has been around a while, but perhaps is growing in interest really. I'm very much interested in how systems of oppression, so by that we mean often discrimination, so sexism, racism, classism, all of these things going on in society, how they act and operate to produce and maintain inequalities in individual outcomes. And crucially, as you can see from the name intersectionality, these things are operating simultaneously and they interact in perhaps complex, unknown ways. And in doing so, they're going to advantage some groups, perhaps white middle-class men, for example, but they will be working negatively and disadvantaging others. And that interaction point's all crucial. So some of the early work was saying, well, the experiences of black women in the workplace aren't as simple, just going, oh yeah, we kind of know that black men are disadvantaged or discriminated against versus white men. And we kind of know that white women have various barriers versus white men. So we take those two bits of knowledge and just sellotape them together. We must therefore understand what happens for black women versus white men. And actually, it's not a purely additive thing, is what's going on. There could be something unique going on in interaction. So, and this is, of course, operating at structural levels, institutions, but also cultural, interpersonal, but also internalized. All this is going on, and things like self-doubt as well. So clearly, most people, would consider this kind of really important to kind of have an eye on the extent to which we have these inequalities, and to try and kind of see what happens to these multiply marginalized groups, and not just to naively assume we know what's going on as well. So there could be something unique going on. And it's also quite an active, an area which encourages activism and campaigning and not just doing research and using policy. Okay. So that's my one slider on intersectionality, and this shifts us into the quant methods, which is what I'll be focusing on here. So the point is, if you want to study intersectionality from a quant perspective, and specifically if you want to kind of map the nature and the magnitude of inequalities and outcomes, average outcomes across many intersections implied by sexism, racism, classism, and the underlying sex, ethnicity, SES kind of type variables and their combinations, many of us would lean towards linear regression to do that. And so we might regress the individual outcome, yi, on gender, ethnicity, social class, X1, X2, X3. And if we're concerned about a gender ethnicity interaction, the black woman having a unique experience, we'd simply put in a two-way interaction. So that's very commonly done. Now, but when people do that, often they won't explore all possibilities. They'll put in a particular two-way interaction of interest, but they won't do a kind of more comprehensive search. And so they might be missing some other kind of combination of characteristics or some where there's more action. And we're assuming that there isn't because we just didn't investigate it. So that's already a little bit of a critique of conventional regression. And so we're failing potentially to make visible what's truly going on, and then you'd be mischaracterizing inequalities. And if you use that as a bit of the evidence base to inform policy making, you might end up suboptimally targeting particular groups. And the concern is it's mostly marginalized groups who kind of typically lose out in this kind of exercise. Okay, so one response to that is, well, let's just switch on the interactions that I'd omitted implicitly previously, and you know, to really kind of speak to intersectionality, I'll switch them all on to get a saturated model. The problem here is, even which are three characteristics and three which are binary, a binary measure of gender, a binary measure of ethnicity, a binary measure of SES or social class, even with that, you end up with three two-way interactions and a single three-way interaction. And it becomes complex substantively to interpret the individual betas. Also, you know, this kind of approach, particularly as you also put in religion or disability in there, ethnicity, shift from a binary measure of ethnicity to some kind of to 6 groups to 10 groups. You know, you very quickly get many parameters, and those parameters are speaking to increasingly small subsets of the data, and so they're estimated increasingly erratically. You're making multiple comparisons, right? Because you're ultimately going to try and compare what's happening in all these different intersections rather than just kind of a priori focusing on one based on theory. And so you run the risk of seeing false positives and over-interpreting them. So regression's got its limits in this kind of application. Now, a partial response perhaps to that is, at least until the part which was about that, hey, you know, it's a bit difficult to interpret these individual betas. Well, what you could do is just use your regression model as a means to an end, as a way to generate the intersection mean. Okay, because the predicted outcome for each individual is simply the mean outcome for their intersection. But if that's all you want, you could just put in 8 dummy variables in the current example, where we have gender, which is binary, ethnicity, which is binary, and social class, which is binary. 2 by 2 by 2 is 8, and so there's 8 intersections, and you could directly estimate their means. But really, if that's all we're doing, then we might as well just use descriptor statistics and just literally just calculate the mean separately for each group. So here I'm just trying to walk through kind of methods that people use and talk about and draw links between them. But hopefully you can see, yeah, things are a little bit unsatisfying here because we've got many small groups, noisy data, erratic estimates, regression models with many parameters. So MAIHDA basically grew out of this kind of these concerns about existing methods. Okay, so let's talk about MAIHDA. So MAIHDA, multi-level analysis of individual heterogeneity and discriminatory accuracy, a very long acronym, is really just a bit of a fancy name, but in some senses, because what underlies it is really just an application of two-level regression. It's a standard multi-level modeling. Having said that, there is something unique and peculiar about it. So if you do a standard multi-level regression in social science, maybe you've got data on student achievement and students are nested within schools, and so you have schools at level 2, you have school effects and so on. Or maybe you have respondents within geographic areas and you're interested in area effects on individual outcomes, or patients within hospitals, hospital effects on individual outcomes. In all those situations, schools, areas, hospitals, these are kind of institutions or geographic areas which are clearly defined and are sitting as pre-existing variables in your data and are natural to explore. What we're doing here is something different. We are saying that the clusters, the schools, hospital areas, are actually intersections in the current analysis. And an intersection is not a variable sitting in a dataset, it is a function of variables sitting in the dataset. It's a function of, for example, gender, ethnicity, social class. You need to construct that variable, and of course there's many choices to make when doing so. And it's the individuals which are nested within their combination of social identities. So that's what gives us a very unusual flavour of multi-level modelling. Nevertheless, underneath the bonnet, it is a multi-level model, which means that we know quite a lot about multi-level models, and we also, they're implemented in standard software. So if you do a MAIHDA, like how do I do a MAIHDA? Well, you just use the multi-level feature of R or Stata or SPSS. So standard multi-level MAIHDA analysis is going to give you four things. First of all, going to quantify with an effect size type measure, what is the importance of intersectional inequalities? How big are they in your study? Okay. Then it's going to allow you to predict and rank the mean outcome across all the intersections. And it's going to do so in a way that we're going to show later is preferable to the descriptive statistic approach. It's going to give more accurate predictions in general. Then it's going to allow us to come to this idea of intersection, which often for many people, they're thinking about interactions, that there's something unique going on different to what we expect. So we're going to see the degree to which intersections follow a purely additive structure, main effect structure, versus is there a need to introduce interactions in some form? And we're not going to be specific as to the exact form, okay? And assuming that we find there's some degree of non-additivity going on, you then want to look at each intersection in turn and see what proportion of it is additive or what proportion is non-additive. Okay, so this method, MAIHDA, was originally proposed by Claire Evans, a colleague of mine, in 2018. So a relatively new method, just 7 years old. And here is a tutorial article that Claire and myself and others published last year, which is probably the best place to go to really, read a journal article length treatment of this with R scripts and Stata scripts. So if you're interested, and hopefully you will be after this talk, please go to that article to find out more. Let's now illustrate MAIHDA. So to do this, I'm going to revisit a paper published by Lena Keller. Now, I wasn't involved in this, but it's a very nice paper, and it looks at intersectional inequalities in students' reading achievement in Germany. Okay, and it does so using the PISA data, which is cross-country comparison data, and they're interested in gender, immigrant status, parental education, and parental occupational level. Okay, so it's a little bit like gender, ethnicity, and social class, really. And you can see the different categories there are for each of those dimensions. 2 by 2 by 2 by 5 gives you 40 combinations, and so individuals are nested within those 40 groups. And we want to map out basically mean outcomes across those 40 intersections. So a few descriptives, just so you get a feel of the data. First of all, the PISA reading score's got this weird and wonderful scale. So the average is around 500 and the standard deviation is 100. But what we can see here is that girls score higher than boys, native students score higher than immigrant, children of parents with higher education score higher, and children of parents in higher occupational classes score higher. So all standard enough patterns. Okay, but those are just kind of looking at each dimension in isolation and looking at means and mean differences. We want to kind of see there's something extra going on when you look at these factors in combination, and that's the MAIHDA approach. So here are the factors in combination. So 40 intersections, she calls them strata, which we have done in our work as well. The first group are the subset of students who are female natives with low educated parents in low occupations. And then we can cycle through all of those characteristics gradually, and once you get to the other end, you're now talking about male students who are immigrants whose parents are high educated and are in high occupation, and there's 74 of those. So how do mean outcomes vary across those 40 groups? So here we wheel out the algebra, okay, the methods talks, a bit of algebra here, but I just want to show you the two MAIHDA models. The first MAIHDA model is simply a two-level, multi-level model with no explanatory variables. And it's going to give us the importance of intersectional inequalities, and it's going to give us our first go at predicting better the mean outcome at each and every intersection, better than descriptive statistics. So the model is simply the reading score for student I in intersection J is models as being equal to a true population mean for that intersection. Okay, and this is the idea that we might only observe 14 students in the intersection, in an intersection, but they are a random sample of all the students in that intersection in Germany. And it's that truth that we're trying to get at. So we're trying to predict that quantity ultimately. And then, of course, student scores deviate from that residuals. So looking a little bit more detail at the truth for a given intersection, this is modeled as being equal to the national average plus an intersection level deviation from that. Okay. So the first thing of interest is how important are intersectional inequalities. That is basically the variance in these true means divided by the total variance in individual scores. And it's going to say what proportion of the total variance is attributable to differences in the true means. Okay, so it goes between 0 and 1, something like 0.1, 0.2, you'll often see in applications, so 10 or 20% of the variability is due to intersectional inequalities. And that's a very interesting statistic which could be compared across countries, across studies, and so on. It's an effect size metric. The second thing that we're trying to get with MAIHDA was the predictions of the intersection means. So these, as I've been hinting at, are more complicated than the simple mean for each intersection y bar. They're actually weighted averages of the small amount of data we might observe on a given intersection, maybe just 14 data points, and the national average. And we do that weighted average because this is basically unreliable. 14 data points is an unreliable small sample to estimate what's truly happening for that intersection. So we combine it with information on intersections in general, as governed by the national average. And so this is a so-called reliability weighted average, where we give more and more weight to what we observe in the sample, the bigger the sample is, effectively. And this idea, of course, shrinkage, empirical Bayes prediction, partial pooling, goes by different names. So implicitly, people who do MAIHDA are kind of saying these are better than those, but no one's shown that formally, but I'll show you that in the second part of the talk. So here are the results from Keller. This first model, she just finds that, hey, 16% of the variation in student reading scores is between those 40 intersections, therefore 84% of variability is within intersection between the individuals. So now that's kind of a standard kind of figure that you might see. This is the second thing, the predicted means for my 40 intersections from left to right. Predicted mean on the y-axis, 40 intersections, yes, from left to right. The red are the girls, the blue are the boys, we've got 20 of each. And then you can see these other kind of groupings at the top. So the 20 on the left are immigrant students with generally lower reading scores, and the 20 native groups on the right with higher. So a couple of things you can see here. The range in predicted scores across the 40 groups goes from about 420 up to around 570. So that's a 150-point range. Now, that equates to 1.5 standard deviations. So even though inequalities only are 16% of the variability, and you might go, well, you're worrying about too much, George, that doesn't sound very important. Well, that min-max range across the 40 groups corresponds to 1.5 standard deviation differential on the underlying reading scores, and that does sound bad. So that's one thing. Another thing is I can actually already see some non-additivity, because we can clearly see the red is above the blue in general. Girls do better than boys, but not by the same amount. The amount varies depending on which other characteristics which are switched on or off. So, here, a little bit better, quite a lot better, a little bit better, worse. Okay. Now, some of this variability might not be significant, but the MAIHDA analysis will help us tease that out as well. But the point is, this is kind of already motivating the need to explore the degree of additivity and non-additivity, which is MAIHDA model 2. Yeah, MAIHDA model 2. So the way we do that is, the change we make to MAIHDA model 1 is to now insert the main effects of gender, immigrant status, parental education, parental occupation in here, just like you do in standard regression. Once you do that, then you basically would decompose the mean, the true mean for a given intersection, into one part implied by additivity and another part which is the deviation from additivity. Okay, so this brings us on to the next kind of statistic, summary statistic, which is, in general, how important is the additive component of this. Okay. And this is something called the PCV. It's basically the variance across the intersections of these predictions based on additivity divided by the total variance. Okay, now this statistic is often very high, 0.9 for example. So often you might see something like 90% of the variation I see between my intersection means, and there's 40 of them here, but there could be hundreds, follows an additive structure. 10% does not. But this brings us on to an interesting thing, which is actually in this model too, which in some sense is preferred because we're putting in more information and very powerful information. The predicted means that we get from this model have a different formula to MAIHDA model 1, implying that they'll take different values. There's still this kind of reliability weighted average of the simple mean for the 14 kids, for example, but we're not doing that as a weighted average of the German national average anymore. Now, rather than German national average, we're saying, well, for each and every intersection, we're going to shrink towards what we expect for that intersection based on additivity, which will, in general, get us closer to the truth than just using the German national average. So we're shrinking to a more sensible point. Not only that, but the degree of shrinkage, whilst has the same form, the parameter estimates change a lot. And so what we're going to do is actually put less emphasis on the data than before, and more emphasis on the model implied quantity, because we're saying that model implied quantity is much better than the German national average. Okay. So you fit that second model, and that's saying indeed here 91% of the variability in those 40 means is additive in structure. So intersectionality doesn't have to have interactions for there to be intersectionality. Okay, because even with no interactions, outcomes are worse, perhaps for Black women than outcomes vary across the 40 groups, and we need to know that. But clearly, there's something unusual going on here to some extent, 10% of the variability. So we could just plot the interactions in isolation. So this is how every intersection deviates from additivity. Okay. Most of these deviations are pretty small. These green lines are plus or minus 10, which is plus or minus 0.1 of a standard deviation. Most are within that, and nearly all of them do not differ significantly from 0. The one exception here is this red one at the end, which is just significant. So this happens to be girls, so native German girls with high educated parents and high occupation. Now, this is the group that the model predicts will have the highest outcome because they've got all the advantages. But when we allow for deviations from additivity, we see that that group actually does even better than that. Okay, so they've already kind of the most advantage based on additivity, and then there's this extra advantage that they're getting. And it's significant because it was statistically significant, but also in magnitude, it's about 0.2, so about 20 points, which is about 0.2 of standard deviation. So, if we didn't look at interactions, we'd miss that. Now, in other studies, more of these may well be significant. Okay, this one was just one. Okay. Okay. So that was part one of the talk, and each part gets a little bit shorter as we proceed. Part two is going to look at statistical advantages of MAIHDA. So, and this is because what we said so far is that, hey, these predicted intersection means from MAIHDA Model 1, they're different from simple means. And then the MAIHDA Model 2 predictions are different again. So we've got 3 sets of predictions which have different formulas, so must give different answers. So, so I've done a paper with Claire Evans and others again, who which really kind of goes to town on trying to understand fully what these models are doing and the different predictions they give and which predictions are most accurate and in what situations. And so I'll give some of the results from this here. So yes, different methods of predicting the intersection means give different answers. So let's just look at that visually with the Keller data. So predicted means on the y-axis, x-axis are the 3 different methods that we're comparing: simple means, what you do traditionally, predictions from MAIHDA Model 1, predictions from MAIHDA Model 2. 40 lines here. I've highlighted in color those intersections which have 20 or fewer individuals, and there are just 6 of those, 6 of the 40. And what you see here is different methods give different answers, but that's clearly especially the case in intersections where there's little data. Okay, if there's lots of data, it's not really going to matter which method you pick. But the point is, we've got a big old data set here, 5,400 individuals, yet 6 out of 40 have fewer than 20. Now, often you might go, yeah, but you know, let's just like not look at the smaller groups. Most of the data, they don't speak to most of the data. Now, the interesting thing about intersectionality is that often it's the multiply marginalized small groups which are most interest. You know, we're not desperately trying to find out what's happening to the kind of white middle-aged man, which is a very large group in this data. We're interested in how these much smaller groups deviate from it. Just because they're small doesn't mean, in number, doesn't mean that they're unimportant. So intersectionality is trying to give more voice to the extremities in the data, in a sense. So it's these kind of lines which are the most important to understand how these methods work for. Okay, so let's zoom in on the purple line. This is intersection 37 with 14 people. Methods 1 and 2, sorry, simple and MAIHDA Model 1 give similar answers, but MAIHDA Model 2 gives something different. So here the scores are 463, 468, very similar, and 497 for MAIHDA Model 2. Now that range is a 34-point range, which is 0.34 standard deviations, a third of a standard deviation difference. So this is really showing that choice of method matters. Okay, for that purple group, clearly it matters even more for orange and for green, and it doesn't matter much for many of the grey lines, okay, but it doesn't matter for some. Okay, so first thing is, why do we get different answers with different methods? And the second thing is, given that we get different answers for different methods, which method should you pick? So let's first answer the why, which is kind of a bit of a mechanical thing. So essentially what we've got here is got the predicted mean on the y-axis, 3 methods on the x-axis, simple, Model 1, Model 2. The simple just gives us 463. That is the average reading score for the 14 kids in that intersection. Now, Model 1 we know gives us something different, and we know it gives us kind of a reliability weighted average of what we observe from that group, 463, and a national average, 478, and the resulting thing is 468. And that green dot, which is what MAIHDA Model 1 gives, it can slide closer to the national average. So if we reduce the number of data points, 14, 13, 12, 11, all the way down to 0, you'd end up here. But if we collected more data on it, we'd kind of go in that direction. Okay, so it's not quite that simple, but that's how you can kind of view this. So MAIHDA Model 2 is again a weighted average of what we observe, but now we are shrinking not towards the national average, but we're shrinking towards something which in general is better, which is the expected outcome for that intersection based on additive main effects, which have very high explanatory power, about 90% of what's going on here. And given that high explanatory power, we therefore get a lot of shrinkage, because we're really saying this is much better than that, or this is a bit better than that, as that determines that the green dot, which is our point estimate, goes closer in that direction. So mechanically you can explain what's going on, but that mechanical explanation doesn't really kind of say which method is best, and certainly doesn't quantify which method is best and how much better and in what circumstances. So that brings us into the kind of analytic derivations that we presented in the paper. So what you could do is a simulation study, okay, where you simulate thousands of data sets according to some kind of true model, and then you predict intersection means based on these three methods, and you compare those predictions across the thousands of data sets to the truth, and that allows you to establish and quantify which is best. We basically do the same, but we do it with algebraic expressions because it's a simple enough analysis that you don't need to go to the rage approach of doing a simulation study. It's kind of overkill. You can do something a little bit simpler with just working with the maths. So what we do is we say that MAIHDA model 2 is the true model. You have to declare a truth to have something to compare against, just like in a simulation study. And we make it the most general of our three approaches because MAIHDA model 1 is a constrained version of MAIHDA model 2, and simple means are a constrained version of MAIHDA model 1. So this is a reasonable kind of thing, perhaps, to make the truth. And then, given that, we can then derive expressions for the simple means, MAIHDA model 1 means, and MAIHDA model 2 means, all in terms of the model 2 parameters, and that allows us to study how variable are our answers across, for example, the 40 intersections versus the truth, how correlated are the predictions from these three methods versus the truth. And we'll do this just in this presentation for the specific case of inequalities. Their importance is that 15% of what's going on is a little bit like an R squared, so similar to Keller, but there's a high degree of additivity similar to Keller. And in the paper, we obviously vary these and talk about the importance of these factors which matter as well. Okay, so we derive some maths, so the analytics, so that's much easier than doing a huge simulation study because the mathematical expressions are relatively simple. And then we plot those expressions and you get nice smooth lines and they tell you what's going on. So in the setup, the true variance in intersectional equalities is 0.15, which is the black line. Okay, and this does not, and that's the truth. Well, that's what we're trying to get to with our methods, blue, red, and green, simple, model 1, and model 2. Calculate simple means, okay, and what you'll see is that the league table of intersection means you get back is going to be two variable. They're going to suggest that there's much bigger intersectional inequalities than the truth, okay, and so we get the wrong answer. Now, that will especially be the case when the intersections are small, or at least some of them are small, as in the current Keller example, where we had 6 of the 40 were 20 or smaller. This is a noticeable bias. Okay. Now, MAIHDA model 1, because of shrinkage towards the national average, leads to less variability, and actually we are now downwards biased. We understate the degree of inequalities. Now that kind of matters, right? Because we might conclude that, there are inequalities, but they're not so bad. That'd be a misstatement. MAIHDA model 2 improves upon that because we're shrinkage to the more reasonable additive structure, and so it's only slightly underestimating the degree of inequality. Interestingly, Keller basically does the red line when they should do the green. And I say that, and what I mean by that is if you go back to their predicted means, that they present in their paper and discuss, these are from MAIHDA model 1 when they should be from MAIHDA model 2. And if they're from MAIHDA model 2, they would be slightly amped up versus this, but that will in general be closer to the truth. Okay, so that's a recommendation from this. The MAIHDA model 2 is preferable, at least on its first criteria. We can also correlate the predictions with the truth. And plot that. And here we want to have a correlation of 1. Okay, so simple means all three methods have correlations less than 1, but MAIHDA model 2 has the correlation closest to 1 because again, it's got more information in it. It's got the additive structure, like so. So again, that's what we should be working with and doing decisions upon. Next up, I want to zoom in on a given intersection. Let's say it's intersection 14 again, which had native males who are low educated parents, low occupation. Hang on, no, there's let's just get it right, George. No, there are low education, high occupation, and that's why perhaps there are only 14 of them, because that's a slight clash there, or unusualness. Okay, so let's say you just want to zoom in on them, and let's play a kind of bit of a thought experiment. Imagine, you know, this result was considered really important, so another researcher comes along and collects the data again to see whether they can replicate. So lots of repeated studies. Okay, so how does that answer vary across repeated studies, and how does that depend on method? So same setup as before, model 2 is a true model, but we're now going to look at across repeated samples, am I getting an unbiased estimate for intersection 37? And how does that depend on method? How does my answer vary? And it will vary, but does it vary a lot or little across repeated samples? And what we'll see is that there's a trade-off. The only way to reduce the variability across repeated samples, because we want a consistent answer, is to introduce some bias. So we get something good by introducing something bad. So the mean squared error is a statistic which puts those two together, and it's a measure of inaccuracy. Okay, so the higher the mean squared error, the less accurate the method. So we want low mean squared error. And we can use that as a criterion for choosing between methods. Okay, so we're going to focus on an intersection with these analytics, which only has 10 individuals, because that's where the action is, small sample sizes. Looking at this plot here, we plot bias on the y-axis. On the x-axis, we've got how much higher is what's truly happening in intersection 37, for example, versus the national average. Now, the blue line is a simple method. So basically, this is saying that across repeated samples, where you take 14 and another 14 and another 14, on average, you're going to get the right answer. And that's irrespective of what that right answer is, whether it's really high or really low. Now, MAIHDA model 1, because it shrinks everything towards the national average, if the truth is above the national average, okay, 0.5 above, for example, it's going to pull it down towards the national average, which is a downwards bias. Hence, the bias line in red is negative, downwards, for high truth. If the truth is below the national average, you're going to be pulled up towards the national average, which is an upwards bias. So on this criterion of bias, simple means are best than the MAIHDA ones. MAIHDA model 2, you know, there's a much more restricted range which we're operating over, because we're now shrinking towards additivity, which does most of the explanatory power, but we're still shrinking, and so if you're below or above additivity, there's still a bias. So let's move on to the second criteria, which is variability. We want to get a similar answer each time. If we get a very different answer each time, then what's the use of the answer from a single replication? So here, simple means method, you're getting a high variance. Okay, so it might be unbiased, which is good, but it's all over the place, which is bad. MAIHDA model 1, yes, it's biased, but at least we're getting something a lot much more consistent across repeated samples. And MAIHDA model 2, even more consistent again. And the degree of consistency in our answers is not a function of whether the truth is above or below the national average or expectations. Sellotape them together to get a combined measure, mean squared error, and remember we like a low mean squared error. What we see is these three lines. And so the simple means basically has the highest mean squared error, really, and unless we're talking about some very extreme scenario where there's a group which has a very high truth, okay, and therefore lots and lots of shrinkage, which actually leads to a less accurate answer across repeated samples than if we just stuck with the basic method. But for the vast majority of intersections, you're going to be much, much better off in MAIHDA model 1, and then even better again with MAIHDA model 2, is what this is saying. This is a summary slide for this section before we shift into the last part of the talk. This tries to kind of sum up what we've said in a kind of slightly more intuitive way. So imagine you are playing darts, right? You're throwing darts at a dartboard and you're trying to hit the bullseye. Okay, so the bullseye is like the true mean for intersection 37, and you're trying to get it, you're trying to estimate it. Okay, and each of those dots are like a different sample. Okay, like a repeated sample. But you've got a blindfold on, so you know kind of roughly where the target is, but you don't really know where the bullseye is. So you chuck it, and you're trying to hit it. The simple method, you can see on average you're unbiased, yay, but you're all over the place, less good. And so really I wouldn't want to bet much money that I'm going to get at all close to the bullseye. Model 1, you're throwing, and now you're much more consistently, you're hitting the dartboard every time, but actually you're a bit off center, and that's the bias aspect. There's low variance, but collectively I'm more willing, Model 1, to bet some money that the one shot I have, the one black dot that really happens, is close to the truth and better than that method. But I can do something even better again, which is my Model 2, which reduces the bias some more in general, and reduces the variability as well, and that is the one that I'm going to pick when I bet that I can get close to the bullseye. So that's kind of what we're talking about here, a bias variance trade-off. Okay, the final part of the talk, part 3, extending MAIHDA. And we're going to shift over to thinking about regression, because if you think about it, all I've done so far is talked about intersectional inequalities in mean outcomes. How does the mean vary across groups? We also want to know how do regression relationships vary across groups, groups being intersections. Okay, so here's the simplest possible example, a linear regression. So maybe we regress reading score on X. Okay, and X could be it could be some kind of homework app or tutoring system, or some kind of text message prompting system to tell the students to do some work or whatever. Okay, and so beta 1 is the positive effect of that intervention. So the question then becomes, does the positive effect of that intervention, which is the average in Germany, does that average differ across subgroups of individuals? But from an intersectionality perspective, interest lies in that fine-grained, nuanced comparison across 40, or it might be 80, 200 kind of groups. Okay, and trying to summarize the variability in that and the structure. So we can do that by extending MAIHDA from effectively an empty two-level model to a model with a covariate X and with a random slope on X. So this is the intersection-specific positive effect of the intervention on the outcome. Okay. And as I said, yeah, you can view this as subgroup analysis, because these are essentially we've got categories, 40 groups, or moderation. You can view it as moderation. So which intersection we're talking about moderates the effect of X and Y. So we're speaking to that. So clearly this opens up new intersectional research questions. To what extent do the regression relationships vary across intersections? A little or a lot. What is the specific relationship for each intersection? Which intersections show the strongest and weakest relationships? Does the direction of regression relationship flip for certain groups? So I said it's positive, but might, for whatever reason, the intervention actually be harmful for one or two groups? No, who knows? And so the example I've given so far is kind of education policy, but health interventions as well. Maybe you've got some text message reminder system to encourage patients to go to their GP appointments when they've been scheduled. And does that text message reminder system have differential uptake across intersections? And for those who take it up, does it have differential effectiveness? And does that depend on disability, ethnicity, geographic region, and their intersections? Employment programs, maybe it's a job mentoring scheme to try and improve employment rates. A lot of people volunteer, but the people who volunteer are diverse in their socio-demographic characteristics, and so age, gender, immigrant status. Is the intervention working equally well for all groups? We're basically, people do this, of course, but typically they'll look at they'll do the analysis, what happens on average, and then, let's look, does it vary by gender, switch gender on, switch it off. Does it vary by urban, rural, switch it on, switch it off. They don't kind of switch on many characteristics, and when they do it, just one at a time. So this is kind of entertaining the possibility of a finer grained, more granular approach. Does the intervention play out in a predictable additive fashion across intersections, or are the results more unexpected, non-additive? Now here's quite a nuanced one. Does the intervention advance or undermine equity? So if you didn't roll out the intervention, clearly we've got a society with intersectional inequalities. Once you roll it out and you measure intersectional inequalities again, have they gone up or gone down? Okay, yes, mean outcome might have gone up, but what about inequality? And all of this kind of fine-grained nuance about what's going on across the distribution might help inform whether you continue to roll out an intervention universally, or you restrict it to certain intersections, targeted, or if you do roll it out uniformly, universally, do you do it in a kind of uniform delivery, or do you customize and tailor the intervention differently to the different needs and requirements of different intersections? So a kind of a MAIHDA layering on top of a conventional analysis might help with these kinds of discussions. So I should say this is just kind of blue skies thinking at the moment. There aren't any papers which do this yet. And so I'm kind of thinking about how to move MAIHDA on in a way which is potentially interesting to this audience. So just to graphically illustrate the ideas, here is the simplest possible analysis you might do. Is the region score boosted by the the homework intervention treatment? Okay. Yes, it is what you'd confirm from this. The intervention works, at least on average, in Germany. Okay. But then a MAIHDA version of this will give you 40 lines, 40 regression lines. And what you can see here is that in nearly all groups, we've got a positive effect of the intervention, but an exception is the red line, where for whatever reason, those who took the treatment actually had a worse outcome afterwards. Okay, so why is that? So within each and every intersection, you imagine that some people are being randomized to get the treatment, some haven't. Okay, treatment and controls. So, there are parallels here to a kind of meta-analysis approach. It's a bit like having 40 separate studies, and each study, each intersection, you've got treated and controls, and they're being randomized, but we're looking at the results collectively. So you clearly want to know, who is that one intersection? Is that significantly negative? Is it significantly different from the others? So the MAIHDA can give you that. But that's one hypothetical scenario. Here's another one where what happens is we still have the same average improvement, but what we've got here is we've got now multiple groups who are negative. Okay, and they've even shifted from having above average outcomes to below average outcomes. So maybe this is, maybe it's some kind of spelling test and a way of teaching spellings, and it just doesn't work for some people. Who knows? Do they have something in common crucially? Because remember, if gender is one of the categories, that will hit 20 out of the 40. Okay, so if there's a subgroup here, maybe it's a specific characteristic which is common to them, and so you can find out what that is, and then perhaps do something different on the intervention for them. Just don't give it to them or change it. Try and understand why it doesn't work and try and improve it for them. Here is a scenario which undermines equity. So initially you look at this and you go, wow, that's great. All the lines are blue. All subgroups improve with the treatment versus the control. Yeah, there's some variability and some improve more than others, but everyone improves, so let's do it. So yeah, sure. But look, the vertical variability in the controls is less than the vertical variability in the treatment. So we've kind of exacerbated intersectional inequalities and undermined a kind of an equity agenda. Here is another scenario. So here clearly the lines pinch together once you have the treatment. So nearly everyone improves, apart from two groups who don't, that you need to check out on, but we have reduced inequalities, and so that sounds good. But are we happy to go with this versus that, given that at least some subgroups will be harmed? Perhaps yes, as long as we do something different for those subgroups. So I'm just trying to conceptually and graphically illustrate some of the different kinds of thinking that a MAIHDA approach layered on top of a very basic kind of individual RCT type setup would give us. So hopefully that was interesting and thought-provoking. So just to conclude in one slide, really, the talk had 3 parts. I introduced MAIHDA. It's really, at least as how it's been used to date, is an exploratory descriptive approach for studying intersectional inequalities across many intersections. It has statistical advantages over descriptive statistics in that the predictions are more accurate. So that was all that middle part of the talk. But really, it's time now for MAIHDA to move on to kind of perhaps more exciting things than just comparing means across groups. You know, and an obvious thing relevant to this audience is subgroup heterogeneity of treatment effects, and getting more fine-grained nuance than perhaps at least some studies aren't currently doing. And in part, that's maybe because you're cutting the data very fine, but that more accurate predictions would apply here as well. So thank you very much. Once again, that's the tutorial paper that we're kind of promoting as a way into this topic with R and status scripts. So do take a look at that. Here is it's on SOC archive. You can Google it. And that's the middle part of the talk. If you love the equations and you want to stare at that, take a look at that paper. And that's it. End of talk. So thank you very much for listening. I hope that was informative.